Good morning. Thank you for joining. I am Gajendra Patro from Tektronix, working as a product line solution AE. Today's agenda is to share details on HDMI 2.1 solutions and standards and their testing challenges. A brief introduction to HDMI 2.1. We'll talk about fixed rate link layer, transmission and receiver measurements, then recommended test equipments, hardware and software configurations, and its advantages. HDMI specification version 2.1 is the most recent update of the HDMI standards, featuring advanced features for the HDMI ecosystem. It supports a range of higher video resolutions and refresh rates, including 8K 60 and 4K 120, dynamic HDR, and increased bandwidth with a new 48G cable. Version 2.1 of HDMI 2.0 specification is backward compatible with the earlier version of HDMI specification. FRL, is known as fixed rate link, is a video signaling technology supported in the HDMI 2.1 specification. This allows for the better transport of audio-video signals. EARC, which is Enhanced Audio Return Channel, is the improvement over audio return channel, that is ARC. With EARC, you will be able to plug your HDMI devices directly into your TV, and the TV will then send the uncompressed high quality audio to soundbar, receiver, or amplifier directly from the EARC port. EARC transmission is the reverse direction to that of HDMI audio video stream. Let me talk about few new things implemented in HDMI 2.1. FRL differs from the traditional TMDS signaling. As we know, HDMI 2.0 and HDMI 1.4 are adapted to TMDS, that is transition minimized differential signaling. FRL uses AC coupled mode, whereas DC coupled mode used in TMDS. FRL rates consisting of 3 to 4 lanes with lane rate of 3 Gbps to 12 Gbps. FRL is backward compatible with lower data rate and will fall back to traditional TMDS if FRL is not supported. FRL can support only predefined discrete data rates such as 3 Gbps, 6 Gbps, 8 Gbps, 10 Gbps, and 12 Gbps on each of its 4 lanes. That means if the data rate is 12 Gbps per lane, FRL can support maximum bandwidth of 48 Gbps, which is about 2.6 times faster than HDMI 2.0. TMDS technologies uses 8B 10B coding method. This method are no longer enough for HDMI 2.1. Hence, it is replaced with 16B 18B coding. Since FRL doesn't require a clock channel like TMDS does, FRL uses 4 pairs of lanes instead of 3 pairs to transfer data. In FRL, you have lane 0, lane 1, lane 2, lane 3, all are data lanes, which corresponds to clock, data 0, data 1, data 2 in the case of TMDS signaling. FRL can support up to 4K at 120 Hz or 8K at 60 Hz, both compressed and uncompressed video contents. Here is the high-level link layer block diagram. FRL adopts VESA DAC compression technology. DAC stands for Display Stream Compression. It uses 16B, 18B encoding to achieve higher through outputs. HDMI 2.1 uses a new packet-based link layer. This layer converts the clock and 3 data lane of original HDMI TMDS mode to 3 or 4 self-clocked links that can be operated at up to 12 gigabits per second. The FRL packetizer separates HDMI data into FRL packets. FRL superblock contains 4 FRL character blocks. FRL character blocks transport one or more FRL packets. Each FRL packet comprises a single map character of 0 to 1022 data characters. Each character block contains up to 502 FRL characters transporting FRL packets and 8 FRL characters carrying Reed-Solomon parity data. Each FRL super block is preceded by a group of 3 or 4 start super blocks that is known as SSB, or a group of 3 or 4 scrambled reset known as SR characters. So SSB and SR characters are comma characters. Both are transmitted on every active lane simultaneously. These are used by a receiver for character alignment. Then it encodes the scrambled data into FRL characters using 1618B encoding. HDMI 2.1 source transmitter testings. There are 9 FRL source measurements and 5 FRL sync measurements defined in the HDMI 2.1 generic CTS. Here are the list of source electrical tests. DC common mode voltage. This is to verify the DC bias at TP1 for each lane. VSE max, VSE min. This measures the singular maximum and minimum voltage. This is also at TP1. T rise, T fall. This test evaluates the transmitter transition time for rising and falling edges. Intra-pair skew. This test measures the difference in time between two FRL data lengths. This is also performed at TP1. FRL rate. This test measures the frequency or data rate accuracy to the nominal FRL rates at TP1. Data jitter. This test evaluates the random jitter like RJ peak to peak and RJ RMS of a FRL link with clock pattern transmitted on the targeted lane at TP1. RJ can be measured in the data I diagram to compensate between 10 to the power minus 6 BER and 10 to the power minus 10 BER and evaluates at TP2 with equalization, which is with cable model and equalizations applied. A data I diagram, which is a single-ended acquisition evaluation at TP2 EQ. This test evaluates the waveform parameter over a significant interval of time to verify that the proper clock recovery and equalizations are applied. A signal quality attributes such that the worst case cable and sync will still result in acceptable viewing performance. AC common mode voltage. This test process verifies the common mode noise of a transmitter. FAP monotonicity. This test verifies that HDMI 2.1 source that can link train to different FAP state, that the FAP parameter pre-shoot, amplitude, de-emphasis are monotonic from one FAP state to the next FAP state. Here are the list of measurements. Link training patterns are required on victim lane and aggressor lanes. The pattern should consist of a required minimum unit intervals and each measurement corresponding to one unit values. LTP1, it is consist of all ones patterns, LTP2 all 0 patterns, LTP3 which is a clock like a 1 and 0 patterns, LTP4 which is 128 zeros followed by 128 1 patterns, LTP5, 6, 7 and 8 are predefined sequence of 4096 FRL characters. Example, HFR 1-3, the duty is required to transmit LTP4 on a victim LAN. At the same time, it must transport the LTP2 like all 0 patterns on the aggressor LAN. And here are the list of different patterns required on victim lane as well as the aggressor lane and the minimum UIs and its low limit and high limits. All measurements are done relatively to a recovered clock. Input clock signal to CRU is the 16B, 18B encoded differential data. Reference CTLE with gain setting from 1 to 8 dB is as per the below definition shown in the graph. Cat3 cable test should be performed with 12G signal by varying CTLE gains from 1 dB to 8 dB. For 3 to 8 dB, 25 mV DFE should be applied. Two channel models are used for worst case model, and there is one short cable model. This is as per the CTS, and I will be rendered for each channel model. The DFE is applicable only at 12 Gbps with worst cable model. Data eye diagram. Crosstalk from the non-target lane is applied using acquisitions for each lane and applying the crosstalk transfer function derived from the channel model. These are summed with the target lane waveform after the differential insertion loss and rendered into one waveform for analysis. Equalization is applied the resulting summed waveform. The data rate at 12 Gbps, the source eye diagram is performed at a TP2 EQ with using CAD3 worst cable model and using 8 dB CTLE and 25 mV DAP. For CAD3 short cable model, it is recommended 1 dB CTLE without DAP. Basically, CTLE and DAP both are applied if data rate is at 12 Gbps. For lower data rate such as 3G, 6G, 8G and 10G, source eye diagram performed with worst case model using 8 dB CTLE and short cable model using 1 dB CTLE without DAP. Crosstalk effect for data eye diagram. The crosstalk from the non-target lane is applied using acquisitions for each lane and applying the crosstalk transfer function derived from the channel models. Please note that there are two cable models defined by the spec, worst case cable model and short cable model. Then these are summed with the target lane waveform after the differential insertion loss and rendered into one waveform for analysis. The equalization is applied the resulting summed waveform. Here are the equation for these cable models. FRL source testing challenges. The maximum data rate goes up to 12 Gbps. Existing test equipment may not be sufficient and needs 23 GHz or higher bandwidth scope and suitable probes. 2.0 fixture cannot be used for 2.1 testing, hence new setup HDMI 2.1 fixture are required. It requires new cable emulation for TX testing. Measurements will need to integrate DAP along with CTLE for two different cable models. EDID needs to be automated. Involves multiple acquisitions, test execution time increases. As for the MOI, it would capture around 90 plus waveforms across 34 acquisitions to run 9 HFR measurements. This is a complex test methodology and it requires all 4 lane testing. Here are the list of test equipments and setup for FRL source testing. 1 or 2 DPO or DPS 70,000 SX with minimum 23 GHz bandwidth are recommended. 4 P7625 Trimode probes are needed for complete automation. If 2 scopes are used, then no probes are required. In that case, we use SMA matched pair cables. A new HDMI 2.1 TPA plug test fixture recommended. These test fixtures are from Wilder. One EDID SCDC controller used for pattern control. Software options are needed such as DJA, option DJAN, option SDLA, and option HDMI 2.1 transmitter solution. So TekExpress compliance software, which is accurate FRL source measurement using precise measurement techniques. Let's look at the dual stack option. 2 4-channel scopes are used. Dual stack scope with SMA cables, 8 synchronized channels, hence no manual reconfigurations. Simultaneous acquisitions and analysis, that means faster through output, no probes. Here is the schematic diagram for dual stack connections. Actual setup picture taken in one of the MOI events shown here. Let's look at the single scope with the Trimode probes options. Use the Trimode capability of the probes P76XX probe series models. We can acquire 2 differential lanes at a time, like a D0 to D2, D1 to D3. We can acquire single end signals also without any connection change. Intra-pair skew measurement can also be performed like D0 to D2, D0 to D3, D1 to D2 and D1 to D3 combination can be calculated. Here is the schematic diagram for scope and probe setup. Let me show you the TekExpress user probe. The TekExpress FRL compliance application gives you the tool to easily run the high definition multimedia interface test under the HDMI compliance test specification 2.1. It displays a complete and reliable solution for quick testings. The TekExpress FRL supports both source and sync measurements. FRL supports only predefined discrete data rates. DOT configuration, test selection, acquisitions, measurement configuration, test results, and the report generation at the end. On the duty panel, select the appropriate EDID or SCDC controller. Currently, the application supports the Alien and Wilder EDID. If you want to control the duty manually, then select the None option. When the None option is selected, the application will show a pop-up every time when either data rate or pattern changes are required. The application will automatically identify the setup, whether it is a dual stack or a single scope with probes. Based on the connection and the display, the multi-lane pop-up comes up accordingly. There are 9 source measurements. All tests can be performed in a single run. Based on the test selected, the required LTP will be transmitted from the DUT. There is option to choose the cable models and equalizations options. Quick pass-fail test is possible with the statistical information about the performed test. A test report is generated at the end. Now here is the HDMI 2.1 sync testing. Sync testing CTS requirements. Perform the link training by sending the link request patterns that LTP on each lane. Switch to video super block once the link is established between source and sync. The super block, which is like a 4 character blocks, each with 510 FRL characters. Read the error counter of each lane to determine the BER. Sync electrical measurements are test ID HFR 2.1, maximum differential swing tolerance. This test confirms that the sync supports the FRL differential voltage at maximum level. Intra-pair skew measurement. This test confirms that the maximum allowed timing skew within each FRL pair is supported by the sync duty. Inter-pair skew measurement. This test confirms that the maximum allowed skew between FRL lane is supported by the sync duty. Minimum link rate tolerance measurement. This test confirms that the sync duty meets FRL link rate tolerance requirement. Jitter tolerance measurement. This test confirms that the maximum allowed jitter is supported by the sync duty. Here are the test lists and their limit values. The first one is about the FRL sync AC input characteristic for 3 Gbps, 6 Gbps, 8 Gbps, 10 Gbps and 12 Gbps. The minimum differential sensitivity for sync to respond is 150 mV for the data rate at 3 Gbps, and at 12 Gbps the sensitivity limit is 100 mV peak to peak after the reference equalizer applied. For the eye diagram, horizontal and vertical limits for all the FRL rates after TP2 equalizer. The input differential swing varies from 150 mV to 1200 mV at 3 Gbps, and at 12 Gbps the swing varies from 100 mV to 1.2 V at TP2. SJT, that is the sync jitter tolerance measurement. This is an important measurement. RJ, the random jitter, the SJ, the sinusoidal jitter, DJ, the deterministic jitter, TJ, the total jitter measurement, performed all the FRL rates. The jitter frequency starts from 100 kHz to 10 MHz, and the peak-to-peak jitter amplitude is limited to 0.1 Tbits. Here is the SJT curve defined, the jitter amplitude versus the jitter frequency. SIP, that is intra-pair skew and inter-pair skew, two measurements with test ID HFR 2-2 and HFR 2-3. Requirement for intra-pair skew measurement is the cable skew of 30 picosecond cascade with the source skew of 0.15 Tbit. That will vary with the data rate. For inter-pair skew measurement, the sync inter-pair skew 4 Tbits plus 500 picoseconds is feasible using the signal source or pattern generation itself or by shifting the patterns. The table shows the SIP requirement, which is like cable skew plus source skew or different data rate. Testing challenges for RX, which is a sync. It requires higher sampling signal source to create pattern at 12 Gbps. Requires a new test fixture to support the maximum data rate. Sync MOI tests are time consuming and it requires multiple connection changes. It requires a calibration and capability for link training. Test results should be based on internal error counter instead of visual assessment. It also requires a different calibration parameters such as differential voltage, inter and intra-phase skew, jitter, then FRL data rate. The sync testing requires a source which is capable of generating a wide range of test patterns and the ability to add a precise amount of impairments to the output signal. The jitter tolerance, skew, sensitivity, and timing testing with repeatability are critical. For customers who want to reduce test time with the performance to meet the new standard requirements, Tektronix offers a complete test solution for HDMI 2.1 sync testing. The Tektronix sync test provides an end-to-end automated solutions with significant reduction in test times. Here are the list of equipments required for sync testing. A real-time oscilloscope with minimum 23 GHz of bandwidth, signal source which is like AWG 70K B model, which is a one channel 50 gigasamples per second AWG. We need four of them because of the four data lengths. HDMI 2 TPAP and HDMI A2 TPAR test fixtures are required. One is plug, the other one is receptacle for calibration purpose. One SC DC EDID controller required. One HD box which consists of delay line, bias T, power supply, etc. Then all these software options such as HDMI 2.1 RX and have option HDM DSM 2.1, then HDM 2.21, then DJA, SDLA, etc. All these options are required for the sync testing. Four AWG 7001B are recommended for sync testing. These AWGs are capable of providing 4 SPU at 12 Gbps to get best jitter granularity. No external plumbing required. Completely automated solution. Intra-phase skew and voltage amplifications are handled using external box. Jitter and cable emulators are handled within the AWGs. Tektronix sync test setup, there is no manual intervention. One-time connect is shown on the figure. AWG HD box, which is programmatically adjust the skew, amplitude, it has inbuilt bias T, power supply, amplifier, delay lines, end-to-end automation including link trainings. These AWGs are best in class, provide jitter granularity. Tektronix sync setup, which has a link training, debugging capability, test link training in advance before starting the test procedure. Uh, when fails, a detailed log file is provided to identify the issue. Use HDMI Express utility tool for closed loop calibration for all 5 measurements. Here is the schematic diagram of sync setup for AWG stack connections. Actual setup picture taken at the MO event. TekExpress user flow for sync. The TekExpress apparel application UI helps the user to generate a wide range of apparel test patterns, and the user can add precise amount of impairments, jitters to the output signals. The test displays a complete link training, and the test result is based on internal error count. Thank you for joining. For any questions, please reach out. I am Gajendra Patro, and my email ID is gajendra.kumar.patro@tektronix.com. Thank you.